Recall that TiKV stores its data in regions. Inside a region, we have replicas. By default, there are 3 replicas in each region. Also by default, if a replica grows larger than 96 megabytes, the region is split. Let's define a few new terms in our Raft consensus algorithms. These terms are leader, follower, and candidate. First up is leader. The leader is the manager of a region. All client traffic passes through the leader. Normally, there is only one leader, and it will periodically send heartbeats to followers to maintain control. When I find out I'm not a leader, I become a follower. Next up, follower. The leader of the cluster will only respond to commands from other servers. Followers take instructions from the leader. After not receiving a response from a leader for a long time, it becomes a candidate. Finally, we have candidate. If something happens to the leader, the followers assume there's a problem. Without a leader, the region cannot function. So all the followers will become candidates, that is, a candidate to become a leader, and initiate a vote to be elected as the leader. In a previous course, we learned that TiKV uses the Raft consensus algorithm to achieve strong consistency of data in a distributed environment. The data in TiDB database can only be written through a Raft leader, and the leader will copy and write instructions to followers in the form of a log. When most nodes of the cluster, and that's important, when most nodes of the cluster receive this log, the log is considered committed and can be applied to the data persistence storage engine, in this case RocksDB. TiDB provides support for 3 replicas by default, and these 3 replicas form a Raft group. Since one Raft group processes a limited amount of data, we will split the data into multiple Raft groups, which we call multi-Raft. The data is split according to key range. We will sort the keys of the data in byte order, that is, a map data structure with an infinite key value, and then split it into continuous key range, each key range as a region. No gap is allowed between 2 adjacent regions, that is, the end key of the previous region is the start key of the latter region. The key range uses an open mode model. The start key belongs to this region, however, the end key belongs to the next region. The TiKV region will have a maximum size limit. When this threshold is exceeded, it will be split into 2 regions. Of course, if there's no data in the region, or if there's little data, it will also be merged with a neighboring region. As mentioned above, multiple Raft groups performed by multiple regions are called multi-Raft. Next, we're going to talk about log replication. When a TiKV client, such as TiDB server, needs to write data, it will send the operation to the leader of the region where the data is to be stored. The leader will encode the operation into an entry and write it to the Raft log. This process is called append. For Raft logs, we can simply understand its format like this. TiKV has multiple regions. We will use the ID of the region as the key prefix in the Raft log, and then bring the Raft log ID to uniquely identify a Raft log. For example, if we now have 2 regions with IDs 4 and 5, then the format of the Raft log is as follows. On our diagram, we have 2 regions. The region to the left has an ID of 4. The region to the right has an ID of 5. Notice that the ID has a key appended to the region number. If we look to the left, the first line is 4_1. 1 is the key. The leader will also copy entries to other followers via the Raft algorithm, which we call replication. When the follower receives this entry, the append operation will also be performed, and the leader append will be notified of success. It is important to understand that append refers to writing the entry to its own Raft log storage, not applying the entry. When the leader discovers that this entry has been appended by most nodes, once again it's most nodes, not all nodes, it thinks that the entry is already committed, and then the operations in the entry can be decoded, executed, applied to the data persistence storage layer, in this case RocksDB. This makes the change permanent. We call this an apply. Previously in this module, we introduced you to the process of copying Raft logs. We mentioned a few actions, namely propose, append, replicate, commit, and apply. Let's sort through these processes together. First up, propose. As shown on the diagram, write requests from clients, such as TiDB server, are converted into Raft logs. For example, in the figure, data with key equals 1 and name equals Tom are inserted into the database. This should be familiar. We covered it in a previous slide. Notice that the 1_1 entry is written to region 1 in the RocksDB KV database. Remember, there are two RocksDB databases on each TiKV node. One stores Raft information and the other stores database data in key value pairs. The next step is called append. Append means that the TiKV node receives the Raft log and persists it in its own RocksDB Raft instance. The log entries are stored locally. However, since we usually have multiple copies of a region, recall by default there are 3 replicas. This is what the replication action does. It copies the Raft log to the remaining 2 replicas. We can see this on the diagram. On to replicate. During the replicate process, the TiKV node, where our leader role region is located, will send Raft logs to the TiKV node where the follower role regions are located. We can see this on the diagram. Take a look at the 2 arrows. When the TiKV nodes with the follower role receives the Raft log, it will persist it to its own RocksDB Raft instance. This process is the same as the append of the node where the leader role region is located in the previous step. Take a close look at the diagram. Do you notice anything different? The arrows have been reversed. If the TiKV node where the region's follower role is located persists the Raft log to its own RocksDB Raft instance succeeds, the message of successful persistence will be returned to the TiKV node where the region's leader role lives. When the majority, that's majority, not all, when the majority of Raft replicas report success, the data is completely persisted on the Raft layer and will not be lost. Next up, committed. The commit we mentioned on the Raft layer is different than what we usually call committed in the application development arena. Our TiKV node packages data in layers. This is similar to the TCP/IP 7-layer protocol. For example, in the figure, the bottom layer is RocksDB Raft and RocksDB KV. This is the data storage layer that stores Raft log and key value pair data. Moving up from the bottom, the next layer is Raft. Above the Raft layer lives the MVCC layer. At the top lies the transaction layer. It is at the transaction layer that our application's transaction is committed. Remember that we said that committed in this sense is not the same as an application development commit. The committed we're talking about here happens at the Raft layer. Committed means that Raft log has been permanently written to the TiKV node in the RocksDB Raft database. Finally, we have apply. After the Raft layer is committed, all we need to do is apply the actions from the RocksDB Raft instance to the RocksDB KV instance. This process is called apply, and it's the last one. As long as the TiKV node where the leader role region is located completes the apply step, then our client, such as TiDB server, will finish writing. After the apply operation, other client sessions can read the data that was just written. Our transaction will only count as committed after the apply is completed, and this commit is the commit on the application on the diagram. Raft divides time into segments of arbitrary length. These segments are called terms. Incremented consecutive numbers are used to identify terms. There is no fixed time for a term. If a candidate wins an election, it becomes the leader. The leader remains in charge until the end of the term. Once again, there is no fixed time for a term. The term lasts until something happens that causes the specific leader to return to the follower state. That something could be the node the leader is on goes down, or their network issues. It is possible, but not likely, for a split vote to create a term that has no leader. In this case, the term number is incremented and a new election starts. The Raft algorithm ensures that a region has one and only one leader. So, when will an election occur? When a TiDB cluster is started, or when a region is created, all nodes in the Raft group are followers. If the followers do not receive a valid message, in this case a heartbeat, from a leader or candidate within a specified time, an election will occur. This specified time is called an election timeout, and it is a random value. So, what is a valid message? A valid message for a leader is a heartbeat message, and a valid message for a candidate is a voting message. There are two variables that control these messages: election timeout and heartbeat time interval. These intervals are designed in such a way as to avoid followers relaunching senseless voting. Assume that node 2 in the figure first breaks the election timeout. It will first increment its term identity, change itself to a candidate role, and vote for itself. At the same time, a voting request is made to other machines in the cluster, and the request contains the term ID that you just incremented. Other followers receive voting requests that contain a term greater than or equal to the current term ID and will update their own term identity and send consent information to the candidate roles node. At this time, the TiKV node with the candidate role receives more than half the TiKV votes, and it agrees to be the leader. Its status changes to leader, and it immediately sends heartbeat messages to all other nodes, and then sends heartbeat messages according to the heartbeat interval. At this point, the first election has been completed. We just described an election timeout triggering a new election. Next, let's assume that the leader of the cluster that is undergoing data replication suddenly goes down or has a network problem. Due to the existence of the heartbeat time interval, that is the leader sending a heartbeat, it is not received for a long time after the leader's heartbeat. There will be followers who increment the term value and change themselves to a candidate. Once a node becomes a candidate, it votes for itself. At the same time, a voting request is made to the other nodes in the cluster. The request contains the term value that was just incremented. As a result, the above voting work was repeated so that a new leader will be selected. Next, let's look at a special case where the election timeout triggers an election. More than two nodes increment their term and change themselves to the candidate role and vote for themselves. And they receive the same number of follower consent messages. What happens? Well, the system will restart a new round of voting until a unique leader is generated. In order to avoid the possibility that a leader will never be elected or elected multiple times, Raft uses an algorithm called random election timeout to reduce the probability of having elections which don't elect a leader. At the time of election, the election timeout is randomly set within the range of using a uniform value. This reduces the probability that an election will result in a tie. Let's look at a few time concepts and parameters. First, we call election timeout, which indicates how long it takes for a node to initiate an election. The first parameter on the list is Raft-election-timeout-ticks. The default value is 10 ticks. This parameter controls the election timeout. Next is the heartbeat time interval, which indicates the number of ticks passed when sending a heartbeat. The corresponding parameter is Raft-heartbeat-ticks, and the default value is 2 ticks. Note that the Raft election timeout ticks and Raft heartbeat ticks parameter are all expressed by the number of ticks. So how long is a tick? The time corresponding to one tick is indicated by the parameter Raft-base-tick-interval, and its default value is 1 second.